Ladies and gentlemen, my name is Sibo Liu. I am a lecturer of this course, Mathematical Analysis. In this course, our object of study is multivariable functions. In many problems, we need to study multivariable functions. For example, every point in this room has a coordinate x, y, z. Once we choose a suitable coordinate systems, okay, then at the time t, the temperature at this point x, y, z will depend on t and the x, y, and z. So the temperature capital T is a function of these four variables. So this is an example of multivariable functions. Now we consider the next example. In this case, as we know, every point in the plane has a Cartesian coordinate x and y, but we can also use the polar coordinate rho and theta. Here rho is the distance from the origin to this point, and the theta is the angle between the arrow from origin to this point with the x-axis. So we know that x equal to rho cosine theta and y equal rho sine theta. Therefore, we have two dependent variables x and y and two independent variables rho theta. Both x and y depend on rho theta. Therefore, they are function of rho theta. So we have a system of functions, two independent variables rho theta and two dependent variables x and y. So this function associate rho theta to x, y. So this is another kind of multivariable functions. It has more than one independent variables and even more than one dependent variables. Okay. So to study multivariable functions, firstly we need to study the domain of definition, which are subsets of Rn, the so-called Euclidean space. I believe we have already learned something about the Euclidean space Rn, but in our first chapter we will review some basic facts about the Euclidean space. So chapter 1, Euclidean space. In the first section of this chapter, we review the linear structure of this space and also the scalar product. So what's Rn? What's our Euclidean space? Firstly, we have a set Rn. Rn is a set consists of unordered real numbers x1, xn. These ordered real numbers are elements of Rn. Xi are real numbers. And we can also use a single letter to denote the element of Rn. Of course, this x is x1, xn. And this xi are called the I coordinate or components of x. So some word about the notation. Some people like to denote the x using the boldface or with a vector symbol. But we don't like this complicated notation. Therefore, we simply denote by x instead of this symbol with the vector or in boldface. We don't like this. Secondly, for the component of x or the coordinate of x, we use xi instead of the lower index xi. We use this and not this one. This notation has some advantage we will realize later. Okay. Now Rn is this set we already understand. Now we will introduce two operations on Rn. The first is addition. Addition is defined below. Suppose x and y are two elements of Rn, then we define x plus y. X plus y is this element also in Rn. It's a new element in Rn whose components are the sum of the corresponding components of x and y. Therefore, the component of x plus y is x1 plus y1 and the xn plus yn. Okay, this is the first operation on Rn called addition. And we also define the scalar multiplication. For scalar multiplication, lambda is a real number and the x is an element of Rn. We want to define the lambda x. Lambda multiplied to x. This is a new element in Rn whose components are lambda x1, lambda xn. So the two operations on Rn had already been defined. Now we will study the basic property of this operation. Firstly, in Rn we have a special element which is 0. This element whose components are all 0. This is a special element in Rn. We call it the origin. Before study the property of the operation, we introduce this special element, the origin. Also, for x in Rn, we can have defined a new element in Rn called minus x, whose element are minus x1. Whose components are minus x1, minus xn. Okay. Now we have this proposition about the properties of the above two operation on Rn. The first one is x plus y equal y plus x. This is obvious by the definition of addition. And also x and y, suppose x and y are elements in Rn, then x plus y is a new element in Rn. Now we added by the third element z. What's this? This will equal x plus y plus z. Associate property. The second statement of our proposition is that for any x in Rn, if we add x by the special element the origin we just introduce x plus 0, we will get x. And if we add x with the minus x, then we get the origin. Okay. The third statement is that the real number 1 multiplied an element x in Rn. What's this? This is equals to x. And for two real numbers, lambda and mu, of course their multiplication is a real number. This real number multiplied an element x in Rn, this will equals to, firstly, we use mu to multiply x, then multiply this with lambda. Now the fourth statement is that for two real numbers, lambda and mu, lambda plus mu is a real number, multiplied x equals lambda x plus mu x. And if we multiply lambda by the sum of two elements in Rn, x plus y, we will get lambda x plus lambda y. Okay, this is all the statement in this proposition. From this result, we conclude that Rn, which the addition and the scalar multiplication is a vector space. So Rn is a vector space under our operation just discussed. So all these are algebra, okay?